Right now, the world's most advanced quantum computers, they look like these massive golden chandeliers.
Yeah, they really do.
I mean, if you follow tech news at all, you've probably seen the press photos. They're gorgeous. These intricate structures of gleaming copper and gold wiring, and they descend layer by layer into this cavernous, extremely power-hungry machine.
Right, the dilution refrigerator.
Exactly. And they require enough electricity to power, like a small neighborhood.
Yeah.
And all of that is just to cool the hardware down to temperatures colder than deep space.
Which is wild to think about.
It is wild, just so the computer can do, a tiny fraction of a second of math before the whole quantum state just collapses.
Yeah, before the decoherence kicks in.
Right. So it's this incredible feat of human engineering, obviously, but it's also, it's fundamentally unsustainable if we want quantum computing to actually scale up. So for today's deep dive, we're looking at a blueprint that essentially takes all that power, all that metal, the brutalist refrigeration, and just replaces it.
Completely throws it out.
Yeah. Replaces it with a levitating 3D printed sponge of pure carbon that's roughly the size of a basketball.
It is an absolute paradigm shift. I mean, we're examining this highly detailed stack of technical white papers and architectural notes. These are from mid-2026, detailing this proposed hardware system. They're calling it the quantum sphere.
The quantum sphere.
Yeah. And the ambition here isn't just to, build a slightly better version of the chandeliers we have today. It's an attempt to just entirely bypass the physical bottlenecks that are crippling the current quantum industry.
Right, the bottlenecks with the traditional flat microchip-style processors.
Exactly. Those planar chips, they just hit a brick wall when it comes to scaling up and staying stable. So the quantum sphere proposes integrating some intensely complex and relatively new fields. We're talking advanced spherical geometry, topological physics, and the really extreme material properties of graphene.
All to house millions of qubits.
Yes, millions of highly stable quantum bits in a single, self-contained, fridge-free unit.
Fridge-free! That's the part that really gets me. So look, if you're a developer or a cryptographer, or just someone fascinated by where computing is actually going next, this is where you want to pay attention. Because our mission for this deep dive is to unpack this hardware from the outside in.
The whole stack.
Right. We're going to figure out how a hollow ball of carbon acts as this impenetrable magnetic shield, how they plan to freeze the electrons without, freezing the actual computer, and how they use magnetic levitation to just isolate the processor from the rest of the universe.
And then we'll get into the actual qubits themselves, which is fascinating.
Oh, yeah, because the documents claim these qubits can hold data for an eternity in quantum time. And then finally, we'll dive into the topological physics that actually crunches the numbers.
It's a really dense stack of source material, I won't lie. But what makes it so compelling is that none of this relies on, imaginary physics.
Right. No sci-fi magic here.
Exactly. Every single mechanism they propose relies on peer-reviewed, demonstrated materials science. The real audacity is just how they plan to integrate all of it into one functioning architecture.
Let's start with the physical object itself, then, the outer shield. Because if we are throwing away the golden chandelier and the giant cryogenic meat locker,
The meat locker, right.
what is replacing it? So the white papers describe the outer structure of the quantum sphere as a hollow shell made of something called graphene aerogel. Now, I know what graphene is. It's that single one-atom-thick layer of carbon arranged in a honeycomb lattice.
Right, exactly.
Famous for being incredibly strong, great conductor. But what actually makes it an aerogel?
Well, to understand an aerogel, you really have to look at how it's synthesized. So normally, a gel is a liquid that's suspended within a solid matrix. Think of gelatin, right?
Sure, like Jell-O.
Exactly.
Yeah.
So to make an aerogel, chemists take a gel, in this case made of graphene oxide, and they carefully extract the liquid part. Usually they do this through something called supercritical drying.
Okay, what does that do?
It basically replaces the liquid with a gas, but it does it without collapsing the solid matrix.
Oh, I see. So you're just left with the skeleton of the gel.
Precisely. You get this highly porous, 3D foam-like structure. And in the case of this graphene aerogel, it is up to 99% empty space.
99% empty space.
Yeah. It has a density of less than 50 milligrams per cubic centimeter. It is phenomenally light.
Wow. It's essentially carbon air.
Pretty much.
But wait, if it's 99% empty space, how does it have the structural integrity to act as a chassis? Like, we're talking about a chassis for a highly advanced quantum computer here.
Right. That's the magic of it, because the remaining 1% is made of carbon bonds, specifically the sesp2 hybridized bonds of the graphene lattice. And those are among the strongest chemical bonds in nature.
So even though it's airy, it's tough.
Extremely. Even when you arrange it in this highly porous, spongy macrostructure, the fundamental atomic links remain incredibly rigid. So you end up with a material that weighs almost nothing but provides immense structural stability.
Okay, so we have this rigid ultralight ball of carbon foam. But the physical structure is just the canvas, right? The documents say this aerogel shell is engineered into a Halbach sphere.
Yes.
Now, I've seen flat Halbach arrays before. You see them in things like magnetic desk toys or high-end electric motors. But how does that translate to a sphere? And why does a quantum computer even need one?
This is where we get into the active shielding. So a standard Halbach array is just a clever geometric arrangement of magnets. When you arrange magnets in a very specific rotating pattern of polarities, the magnetic fields actually interfere with each other.
Like waves in a pool.
Exactly. On one side of the array, the fields constructively interfere. They augment and strengthen the magnetic pull. But on the other side, they destructively interfere. They essentially cancel each other out to near absolute zero.
Right, so you get a magnet that only sticks on one side and the other side is just magnetically dead.
Yes. Now, take that mathematical principle and project it onto a 3D spherical geometry.
Okay, wrapping it into a ball.
Exactly. But instead of using permanent solid magnets, the quantum sphere uses a highly specific rotating pattern of electrical currents flowing over the surface of the spherical aerogel.
Oh, so it's an electromagnet.
Right. And by continuously driving these currents, they generate a perfectly uniform magnetic field inside the Hawley center of the sphere. The white papers actually target about 0.2 Tesla for their prototype. But the really crucial part is the destructive interference on the outside.
So the sphere projects exactly zero magnetic field outward.
Zero. Nothing leaks into the room.
Which means, conversely, nothing from the room leaks in.
Bingo. By Lenz's law and the properties of that continuous conductive shell, it acts as an absolute magnetic shield against external fluctuations.
Wow.
It creates this silent, perfectly shielded sanctuary inside the hollow center. The delicate quantum bits inside are just completely isolated from the chaotic, noisy, magnetic environment of the outside world.
So things like Wi-Fi signals or the Earth's magnetic field?
Or even just nearby electronics, none of it gets in.
Okay, conceptually, that is brilliant. The shape itself becomes the shield. But I have a massive logistical question here. You said they use precise electrical currents flowing over the surface of the sphere to create this field.
Yes.
How do you wire precise, complex electrical circuits onto a sponge made of carbon air? I mean, you can't exactly solder copper wire to an aerogel.
No, you definitely can't. And this is honestly one of the most elegant fabrication techniques in the documents. They manufacture the circuitry directly out of the aerogel itself.
Wait, out of the foam?
Yeah. It starts with a 3D printing technique called direct ink writing, or DIW. They formulate a special viscoelastic ink made of graphene oxide flakes, and they print the coarse, spongy, spherical scaffold.
But graphene oxide isn't a great conductor, is it? Doesn't the oxygen get in the way of the electrons?
That's the key. Graphene oxide is essentially an insulator because the oxygen functional groups disrupt that beautiful conductive honeycomb lattice. So after they print the sphere, they put it under a specialized femtosecond laser.
A femtosecond laser, meaning it fires really fast.
Incredibly fast. It fires pulses of light that last for quadrillionths of a second.
A quadrillionth? Why on earth does it need to be that fast?
Because of thermal diffusion. If you hit this fragile aerogel with a continuous laser, the heat would just spread and it would melt or burn the entire structure.
Oh, right. It would just catch fire.
Basically, yeah. But a femtosecond pulse deposits a massive amount of energy so incredibly fast that the chemical bonds break before the heat even has time to spread to the surrounding atoms.
Wow. It's like a surgical strike at the atomic level.
That's a great way to put it. The laser specifically targets paths on the sphere, and the intense, localized photon energy violently strips the oxygen atoms away from the carbon. This process is called photothermal reduction, and it restores the pure graphene lattice exactly where the laser hits.
So let me get this straight. They are literally drawing the conductive wires into the structure of the foam with light.
Yes, they selectively change the chemical properties of the aerogel to create these incredibly complex 3D rotating current paths.
That is insane.
Right. There are no separate copper wires, no glues, no soldering. It is a single monolithic material. And this is vital because whenever you try to bond two different materials together in quantum hardware, You introduce thermal mismatch and atomic defects, and that generates noise. The monolithic design just completely eliminates that.
Okay, so we have this ultralight, magnetically shielded, laser-printed sanctuary. But that brings us to the elephant in the room, which is temperature. Because the entire reason quantum computers look like giant chandeliers today is because of the dilution refrigerator.
Big chillers, yeah.
Right, those rigs draw anywhere from 10 to 26 kilowatts of power just to cool everything down to about 10 to 20 millikelvin. Why is this new sphere any different? Doesn't quantum hardware inherently require deep space temperatures to function?
Well, yes, the quantum data carriers, the electrons themselves, they absolutely must remain near absolute zero. But the quantum sphere challenges the assumption that the entire computer needs to be at absolute zero.
Oh.
Yeah. The white papers detail a paradigm shift they call on-chip local cooling.
On-chip local cooling. How does that even work? You can't just put an ice cube on a microchip.
No, but it relies on understanding what actually needs to be cooled. In traditional systems, to ensure the electrons are at 10 millikelvin, you have to cool the chip, the substrate, the wiring, the brackets, literally the entire structural lattice of the machine down to 10 millikelvin.
Right, it's just brute force global cooling.
Exactly. But the quantum sphere, however, places the outer shell and the physical processor in a much warmer environment. We're talking around 300 to 500 millikelvin.
I mean, 500 millikelvin is still incredibly cold for a human, but compared to 10 millikelvin, I guess it's practically balmy.
It's a massive difference in energy. I mean, achieving 500 millikelvin only requires a standard, commercially available 4 Kelvin pulse tube cryocooler.
Which is way smaller.
Vastly smaller, cheaper, and way less power hungry than a full dilution refrigerator.
But wait, hold on. If the physical chip is sitting in a 500 millikelvin environment, the electrons inside it are naturally going to heat up to 500 millikelvin, right? And then they'll lose their quantum state.
They would, yes.
And the documents say the electrons need to be below 50 millikelvin. So how can you have electrons that are 10 times colder than the actual material they are sitting inside?
This is where they use a mechanism called tunnel junction coolers.
Okay, unpack that for me.
So during the fabrication of the processor, they deposit these tiny superconducting contacts. They're usually made of aluminum or niobium directly onto the graphene. When they apply a very specific voltage bias across these junctions, they trigger a quantum mechanical process called selective tunneling.
Selective tunneling. Okay, I really need to understand the physical mechanism here. How does a piece of aluminum selectively filter heat?
It has to do with the energy states of the materials. So when a metal like aluminum becomes a superconductor, it develops what physicists call an energy gap.
An energy gap.
Yeah. Think of it as a massive wall in the energy landscape. Electrons can't easily exist at energy levels inside that gap. Now, inside the graphene processor, you have a population of electrons. Some are low energy, which means they are cold. And some are high energy, meaning they have absorbed thermal energy from the environment. They are hot.
Okay, so you have a mix of hot and cold electrons just bumping around in there.
Right. And they are bouncing against that superconducting aluminum junction.
Mm-hmm.
Because of the voltage bias they apply, the energy levels are perfectly aligned so that the hot electrons have just enough energy to jump over that gap, or more accurately, they quantum tunnel through it.
Into the aluminum.
Yes, into the aluminum. But the cold, low-energy electrons, they don't have the energy to make the jump, so they just hit the wall and bounce back.
That is wild. That operates almost exactly like evaporation.
Evaporation? How so?
Like when you have a hot cup of coffee,
Right. Yeah.
The most energetic water molecules evaporate as steam, and the liquid left behind in the cup is physically colder because the overall average energy just dropped?
Yes. That is a phenomenal analogy. It is essentially quantum evaporation. They are siphoning off the heat, literally electron by electron. And it is breathtakingly efficient.
How efficient are we talking?
The white papers cite a voltage to temperature transfer rate of up to negative 115 Kelvin per volt.
Wow.
Yeah. This selective extraction drops the remaining electron population in the graphene to below 50 millikelvin. It effectively thermally decouples the electrons from the physical lattice of the chip.
I really want to make sure you, the listener, grasp the implication of this. Because standard quantum cooling is it's like air conditioning an entire skyscraper. You know, pumping millions of watts of cooling power into the concrete and the walls and the floors just to keep one single server room on the top floor cold.
Which is horribly inefficient.
It is a massive waste of thermodynamics. But what the quantum sphere is doing with these tunnel junctions is letting the skyscraper sit at basically room temperature
Hmm.
and just giving the processor an ice-cold drink from the inside.
Exactly. It targets the cooling directly at the data carriers themselves.
But wait, thermodynamics is stubborn. Even if you are constantly siphoning off hot electrons, the chip itself is still physically sitting in a 500 millikelvin environment. Heat conducts.
It does.
So why doesn't the ambient heat of the physical lattice just instantly bleed back into the electron population and totally overwhelm the tunnel coolers?
Because of the extreme properties of graphene, this is where the whole system really starts to integrate beautifully. Graphene is one of the best thermal conductors known to science.
Right.
It has a thermal conductivity between 2,000 and 5,000 watts per meter Kelvin. So as the tunnel junctions extract the hot electrons, the massive surface area of the graphene aerogel shell acts as a hyper-efficient heat spreader.
Oh, I see.
Any residual heat, whether it's from the environment or from the computational operations themselves, which is called Joule heating, it is instantly wicked away and distributed across the porous shell.
So the material itself acts as the heat sink.
Yes, whisking thermal energy away way faster than it can coupled to the fragile electron population.
If this actually works, the implications for the industry are just staggering. Because if you don't need a 26 kilowatt cryogenic plant to run a quantum chip, you don't need a specialized national laboratory or a massive tech campus to house it.
No, you really don't.
The footprint of a quantum computer shrinks to the size of, like, a standard commercial HVAC unit. It fundamentally democratizes who gets to own and operate quantum hardware.
It really moves quantum computing out of the bespoke laboratory phase and into real commercial deployment. However,
There's a catch.
there is a physical catch. To truly maintain this thermal decoupling, you can't just bolt this processor to the warmer outer shell.
Right, because any physical connection, a screw, a bracket, a wire, is a highway for heat.
Exactly. In solid-state physics, heat travels through a material via phonons, which are just quantized units of mechanical vibration. Every atom in a solid lattice is vibrating, and that vibration ripples through the material.
So if you bolt it down,
If you have physical tethers holding the chip in place, acoustic phonons from the warmer shell will constantly bombard the processor, and that causes the quantum states to decohere.
so if you can't touch it, how do you hold it?
You remove the connection entirely. The quantum sphere relies on contactless computation. The processor is suspended in a vacuum with absolutely no physical tethers whatsoever.
Okay, this is getting crazy. We are now looking into the dead center of this hollow 500 millikelvin magnetically shielded sphere, and right in the middle is the processor,
The floating brain, as the documents call it.
the floating brain. It's a microgram scale chip made of bilayer graphene, and it's completely encapsulated in hexagonal boron nitride, or HBN. And it is levitating.
Levitating.
How are we talking about standard magnets just pushing against each other?
Not standard ferromagnetism, no. It utilizes a phenomenon known as diamagnetic levitation.
Okay, I think most people have an intuitive grasp of ferromagnetism, like a magnet sticking to a fridge door. How is diamagnetism different?
Well, ferromagnetic materials have unpaired electrons with magnetic moments that really like to align with external magnetic fields. That's what pulls the material toward the magnet.
Right, they want to stick together.
Diamagnetic materials, on the other hand, actively repel external magnetic fields.
They push away.
Yeah. When you expose a diamagnetic material to a magnetic field, the field actually alters the orbital motion of the electrons inside the material. These altered orbits create microscopic induced electrical currents.
Okay.
And those currents, in turn, generate their own magnetic field that perfectly opposes the applied field.
So the material generates a mirror image magnetic force pushing back. It fundamentally just hates magnets.
Yes. And graphene, particularly bilayer graphene, has an incredibly strong diamagnetic response because its electrons can easily flow through those hexagonal rings, creating very strong induced orbital currents.
But wait a second. Earlier, we established that the Hallback sphere creates a perfectly uniform internal magnetic field to shield against noise.
We did.
A uniform field pushes equally from all sides.
Yeah.
If the chip is pushed equally from every direction, it doesn't levitate, it just sits there. To get levitation to counteract gravity, don't you need a stronger push from the bottom?
You are absolutely right. Levitation requires a magnetic field gradient, a spatial difference in magnetic field strength that creates a net upward force.
So how do they get a gradient inside a uniform shell?
By returning to that femtosecond laser printing we talked about.
Oh.
Yeah. When they draw the conductive current paths on the inner surface of the aerogel shell, They don't just create a perfectly symmetrical Halbach array. They deliberately pattern very specific, localized imperfections, radial magnetic field gradients directly into the surface currents.
Sneaky.
Very. By fine-tuning these paths, they create targeted gradients of about 0.5 to 2 Tesla per meter near the center of the sphere. And because the encapsulated bilayer graphene chip is so unfathomably light, weighing only micrograms, this tiny localized upward magnetic pressure perfectly counteracts the downward pull of gravity.
And the chip floats.
The chip floats.
It's literally microscopic hoverboard technology.
Yeah.
But honestly, balancing something on a magnetic gradient, it sounds like trying to balance a marble on top of a bowling ball.
It is incredibly delicate.
Right. Like any slight breeze or vibration, and it's going to slide off center and just crash into the wall of the sphere.
Yeah.
How does it stay perfectly still?
That is the big engineering challenge of levitation. So the quantum sphere employs a two-pronged approach: passive and active stabilization.
Okay, let's start with passive.
Passively, the chip is fabricated with edge-thickened diamagnetic rims. Think of them as magnetic bumpers.
Bumper, okay.
If the chip starts to drift away from the dead center, these thicker edges encounter a stronger part of the magnetic gradient. That
Right.
generates a stronger repulsive force that just nudges the chip back into the valley of the field.
Okay, so it's sitting in this invisible magnetic ball. What about the active stabilization?
The active stabilization is arguably the most elegant part of the entire physical design, because it requires no moving parts and no computer intervention whatsoever. It relies entirely on Lenz's law and eddy currents.
Okay, you're going to have to explain Lenz's law. Because if I remember high school physics, if I move a magnet through a copper pipe, the magnet falls really slowly. Is that what we're talking about?
That is the exact macroscopic version of this microscopic phenomenon, yes.
Yes.
So Lenz's law states that when a conductive material moves through a changing magnetic field, it induces an electrical current, an eddy current, inside the material.
Okay.
But crucially, that induced current creates its own magnetic field, and the direction of that new field always opposes the motion that created it.
So as the magnet falls, it creates an electrical current in the copper pipe.
Mhm.
And that current acts like a magnetic brake pushing up against the magnet.
Exactly. The kinetic energy of the falling magnet is literally converted into electrical energy, which then dissipates as minute amounts of heat in the pipe, and it kills the momentum. The quantum sphere uses this exact principle. If the levitating graphene chip starts to wobble or oscillate due to some tiny environmental vibration, its movement through the static magnetic gradient immediately induces eddy currents within the graphene.
And those eddy currents instantly generate an opposing force, dragging against the motion.
Yes.
So it creates its own brakes.
Exactly. It is an inherent self-damping mechanism. The chip stabilizes itself simply by the act of trying to move. It rapidly dampens any oscillation without any physical contact at all, coming back to a dead stop in the center of the vacuum.
This is just staggering. The physical mechanics of the universe are doing all the heavy lifting for the engineering. And by achieving this perfect, stable levitation, they have totally solved the phonon problem.
Yep.
Because it's hanging in a vacuum with no wires, there's absolutely no physical path for acoustic vibrations from the outside world to reach the chip and scramble the quantum data. Is the ultimate noise isolation.
It is entirely mechanically decoupled from the universe.
But here is where my logic hits a wall.
Okay, let's hear it.
We have isolated this chip perfectly. It's floating in a vacuum, completely untethered, but it's still a computer processor. We have to give it instructions, and we have to extract answers. If there are no wires, how do you talk to it? I mean, you can't exactly plug an Ethernet cable into a floating microgram chip.
No, you can't. You communicate with it electromagnetically across the vacuum gap. They use precisely calibrated microwave pulses.
Microwave pulses, so it's basically quantum Wi-Fi.
Effectively, yes. Look again at the laser pattern tracks on the inside of the aerogel shell. Some of those tracks are engineered to act as 3D coplanar waveguides.
What's a waveguide?
A waveguide is essentially a structure that guides electromagnetic waves. It directs the energy exactly where you want it to go, rather than letting it radiate randomly in all directions.
Oh, like a fiber optic cable, but for microwaves.
Exactly. These waveguides on the inner shell act like highly directional microscopic radio towers. They beam specific microwave pulses through the cold vacuum directly at the floating brain.
And the chip receives it.
Right. The antennas on the encapsulated chip receive these pulses, which then execute the quantum logic gates on the electrons.
Okay, so we are beaming instructions to a floating chip. This is actually the perfect moment to shift our focus to the qubits themselves. What are those microwaves actually interacting with? We really need to talk about the data storage because earlier we teased a metric about how long this system can hold data, and frankly, it sounds physically impossible based on what current quantum computers can do.
It is a massive leap. Let's establish the baseline first. In this architecture, a qubit isn't a loop of superconducting wire like a transpon, which is what companies like IBM use.
Right.
In the quantum sphere, a qubit is a single individual electron physically trapped in what is called a gate-defined quantum dot within that suspended bilayer graphene.
Okay, what exactly is a quantum dot?
Think of it as an artificial atom. By applying localized electrostatic voltages to the HBN encapsulating layers, they create tiny energetic valleys, potential
Those
wells.
little dips.
Yeah, and these wells are so small, and the repulsive forces are so tight that they can trap exactly one electron inside. So one trapped electron equals one physical qubit.
Okay, we have our trapped electron. Now, the metric we care about is the relaxation time, right? What physicists call T1.
Yes. The T1 coherence time is arguably the most critical metric in all of quantum hardware.
Why is that?
It measures the lifespan of the quantum data. If you put a qubit into a specific high-energy state, a one-flame meadow, how long can it maintain that fragile state before spontaneous emission or environmental noise causes it to relax back down to the ground state, a zero?
And when it relaxes, your data is gone.
Exactly.
And what is the standard lifespan for the superconducting qubits we have today?
The T1 time for a standard transmon qubit is typically measured in microseconds.
Microseconds.
Yeah. A microsecond is 1/1,000,000th of a second. So somewhere between 10 and 300 microseconds is the current industry benchmark.
That means the computer has to execute all its logic, all its math, and read the answer before a fraction of a millisecond passes. Or it just forgets everything it was doing.
Right. It's a frantic race against the clock.
But what do the quantum sphere white papers claim for these suspended graphene qubits?
The documents cite a projected T1 relaxation time of 30 to 38 seconds.
Seconds.
Whole seconds.
Over half a minute. I really want the listener to grasp the scale of that. That is an improvement of roughly 100,000 times over current state-of-the-art.
It's game-changing.
If you are a software developer trying to write quantum algorithms for logistics or cryptography or drug discovery, a 30-second coherence time means the hardware is no longer your bottleneck. The system isn't racing against the clock of its own death. But how? How do you take an electron and protect it so thoroughly that it lives 100,000 times longer?
It is achieved through something called Kramers-pair protection.
Kramers-pair protection.
To understand this, we have to look deeply at the properties of electrons in a graphene lattice. An electron isn't just a point of charge, right? It has several degrees of freedom, which are just different ways it can exist and carry information.
Okay.
The most common one is spin. You can loosely visualize it as the electron spinning on its axis, either pointing up or down.
Right, spin up is a 1, spin down is a 0. That's standard quantum mechanics.
But graphene is special. Because of its unique hexagonal honeycomb atomic structure, an electron in graphene has an additional degree of freedom called a valley.
A valley, like a physical valley between two mountains.
Not physical space, but momentum space.
Okay, you lost me.
In solid-state physics, we use a mathematical construct called momentum space, or K-space, to map out the momentum states available to an electron in a crystal lattice. When you map the energy bands of graphene, they form these distinct cones that touch at specific points, called Dirac points.
Still pretty abstract, but go on.
The two distinct valleys in this momentum landscape are typically labeled K and K prime. So an electron can exist in the K valley or the K prime valley.
Okay, so it has spin, which is up or down, and it has valley, which is K or K prime. What does the quantum sphere do with that?
It weaves them together. Instead of just using spin to store data, they encode the data into a combined spin valley state.
We're combining them.
Yeah. For example, the logical zero state isn't just spin up. It is the electron sitting in the K valley, A and D spinning up. And the logical 1 state is the electron sitting in the K prime valley, A and D spinning down. This specific combined state is called a Kramers-pair.
So they're linking these two properties to create a super property. But why does linking them suddenly grant 30 seconds of immunity from noise?
Because of a fundamental physical principle known as time reversal symmetry.
Time reversal symmetry. All right, I need you to translate that. Are we talking about time travel?
Not quite time travel, no. Time reversal symmetry is a mathematical test. It essentially states that if you were to play the physics of a specific system backward, like rewinding a movie, the fundamental laws governing the particles would look exactly the same.
Right.
In quantum mechanics, a theorem called Kramers' theorem dictates that in any system that obeys time reversal symmetry, half-integer spin states like our electrons must be doubly degenerate.
Doubly degenerate meaning they exist in pairs with the exact same energy level.
Exactly. Because the k spin-up state and the k prime spin-down state form a Kramers-pair, they are fundamentally linked and protected by the symmetry. Think about what a piece of environmental noise like a rogue magnetic fluctuation or a stray phonon would have to do to cause an error and flip the qubit from a 0 to a 1.
Well, we have to flip the spin.
Yes, but because the state is linked, it can't just flip the spin. It has to simultaneously flip the spin from up to down, and apply a massive momentum kick to scatter the electron all the way across momentum space from the K valley into the K prime valley.
Oh,
Ah.
I see. And random background noise doesn't have the highly specific coordinated energy profile to do both of those things perfectly at the exact same time.
Precisely. Standard environmental noise usually couples to either spin or charge, but it fundamentally lacks the complex structure required to simultaneously trigger a massive momentum transfer and a spin flip in a way that breaks time reversal symmetry.
Wow.
The symmetry itself acts as an invisible, impenetrable shield. The noise simply cannot see the data to interact with it.
Let me try to put an analogy on this just to ground it. Standard superconducting qubits, the ones that die in microseconds, they're like spinning plates on sticks. You, as the computer, have to constantly rush around, applying massive amounts of control energy just to keep them perfectly balanced because the slightest breeze of thermal noise knocks them over.
That's a great way to picture current tech.
Right. But a Kramers-pair qubit is like a heavy titanium gyroscope locked inside a vacuum field vault. You spin it once, and it just keeps spinning perfectly for half a minute because there is physically nothing in the environment capable of reaching in and slowing it down.
That's exactly right. And the implications for the broader system design are profound, particularly when it comes to error correction.
Right, because in current quantum computers, if your qubits are dying every 100 microseconds, you have to dedicate an enormous amount of your processing power just to checking for errors before the data vanishes.
The overhead is crippling. In standard planar systems, you might need 1,000 physical qubits working together in a complex surface code just to create one reliable, error-free logical qubit. For the vast majority of the machine is just doing maintenance on itself.
It's all just janitorial work.
Basically, yeah.
Yeah.
But if your qubits naturally hold data for 30 seconds due to Kramers-pair protection, that overhead plummets. The white papers project needing only 100 to 200 physical qubits per logical qubit. It makes scaling the machine drastically more realistic.
But isolating the chip and holding data for 30 seconds is only half the battle, right? I mean, hard drive holds data, but a computer has to actually process it. We have to do math.
Yes, we do.
So how do you force these ultra-protected, isolated electrons to interact with each other without accidentally breaking the symmetry and destroying them? This requires perfect logic gates, which moves the quantum sphere into the strange, almost alien realm of topological physics.
Yes, it really does. If Kramers pairs are how the quantum sphere stores memory, topological physics is how it processes that information. And this is where the theoretical leaps in the white paper are the most intense. The architecture relies on non-abelian ennions.
Okay, I have to stop you. Non-abelian ennion sounds like a sci-fi MacGuffin.
It does sound made up.
What actually is an ennion, and what does it mean to be non-abelian?
Okay, let's start with the standard model of particle physics. In our 3D world, all fundamental particles fall into two strict categories based on their quantum statistics. Fermions, like electrons and protons, which make up matter, and bosons, like photons, which carry force.
Right, matter and force.
But physics gets weird when you restrict it to 2 dimensions.
And our bilayer graphene chip is fundamentally a 2D environment.
Exactly. The electrons are trapped in a 2-dimensional plane. In 2D systems, the mathematical rules of quantum mechanics loosen up, allowing for the existence of quasiparticles that don't fit into the fermion or boson categories.
They break the rules.
Yeah, they can have fractional charges and exhibit fractional statistics because they can be anything in between. Physicists cheekily called them ennions.
Okay, so they are these weird fractional particle ghosts that only exist in 2D planes. What about the non-abelian part?
That refers to how these ennions behave when you move them around each other. So if you take two identical regular particles in 3D space, like two electrons, and you swap their positions, the overall quantum state of the system doesn't change in any meaningful, observable way.
They're interchangeable.
Right. But if you swap the positions of two non-abelian anyons, the entire quantum state of the system shifts to a fundamentally new, distinct state. The order in which you swap them actually matters.
So swapping particle A then B leaves you with a different reality than swapping B then A.
Exactly. Specifically, the quantum sphere utilizes a type of non-abelian enyon called a Majorana zero mode, which is a quasi-particle that acts as its own antiparticle.
Wow.
But here is the breakthrough for quantum computing. Instead of trying to process data by changing the local fragile state of a single electron, like forcing it to flip from spin up to spin down, the quantum sphere encodes data globally in the physical arrangement or the topology of multiple Majorana zero modes.
Topology, meaning the shape or the spatial relationship of the particles to each other.
Right. And to execute logic gates to perform addition, subtraction, or search algorithms, the microwave pulses we talked about physically or effectively move these anyons around each other in specific choreographed sequences in 2D space over time.
Like braiding hair.
That is the exact mathematical terminology. They braid the anyons' world lines together. The mathematical operation is the physical braid.
Let me try to put a grounded analogy on this because it is difficult to visualize.
Go for it.
If I have data stored locally, in a traditional way, it's like my data is encoded in the color of a shoelace. If a drop of mud falls on the shoelace, the color is ruined, the state is changed, and my data is lost. That is a local error destroying local data.
Makes sense.
But topological data is completely different. It's like my data is stored in the fact that the shoelace is tied into a complex double knot. If a drop of mud falls on the knot, it doesn't matter. It does nothing to the knot. It is still a double knot.
Exactly.
The information isn't in the local string itself. The information is in the global topology of the knot.
That is a phenomenal analogy, and that is the holy grail of quantum mechanics. Local errors, a stray photon, a thermal vibration, a tiny spike in the magnetic field cannot destroy global topological information. A local noise event cannot accidentally untie a complex knot. To destroy the braided data, the environment would have to provide a massive amount of highly coordinated energy to perfectly unbraid the entire system globally, which is statistically impossible. This is why topological quantum computing guarantees fault tolerance at the foundational hardware level.
So the hardware flaws simply don't matter to the software. The math is protected by the physical geometry of the universe itself.
Exactly.
But for this to work, you have to be able to move these anyons around the chip to braid them. You need wires connecting the different quantum dots. And normal wires have resistance, right? Electrons bump into impurities, they lose energy, and they create heat. How do you move these protected topological states without destroying them in transit?
To achieve that, the quantum sphere relies on another profound topological phenomenon, the quantum anomalous Hall effect, or QAE.
Unpack QAAG for me. What is it, and how does it act as a perfect wire?
Well, the goal here is dissipationless transport. We want electrons to flow from point A to point B with literally zero electrical resistance and zero energy loss. The quantum anomalous Hall effect allows for this, but only along the very outer edges of the 2D graphene material.
Just the edges.
Yes. It is driven by a mathematical concept called Berry curvature.
Berry curvature. I assume named after a physicist, but what is it actually curving? You mentioned momentum space earlier.
Yes, named after Sir Michael Berry. To understand it, think about how we map reality. Normally we map physical space where things are, but as we discussed with the valleys, physicists often map momentum space, or K-space, to see how things are moving. Berry curvature is a geometric property of the quantum wave functions mapped in that momentum space.
That's pretty abstract. What does Berry curvature actually do to an electron moving in the real world?
In the real world, if an electron possesses this Berry curvature, it acts exactly like a massive internal magnetic field. It grabs the electron and forces it to experience an anomalous velocity that pushes it to the outer boundary of the material.
Pushes it to the edge.
Yeah. Practically, it forces the electrons into strictly one-way lanes that run right along the perimeter of the bilayer graphene. These are called chiral edge states.
One-way lanes, meaning the electrons are physically forbidden from turning around.
They absolutely cannot turn around. Because quantum mechanics restricts them to moving in only one direction along the edge, they physically cannot backscatter.
Backscatter.
Yeah, like If an electron in a chiral edge state hits a microscopic impurity or a defect in the carbon lattice, it doesn't bounce backward because there is no quantum state available for it to move backward into. It just flows perfectly around the defect, like water flowing effortlessly around a smooth rock in a fast river.
Because it can't bounce back, there is zero resistance and therefore zero energy lost as heat. It is a mathematically perfect wire.
Perfect wire.
But the outline for the device notes that this requires something called proximity-induced spin-orbit coupling. Now, pristine graphene doesn't have strong spin-orbit coupling on its own, right? It's just like carbon.
Correct. Carbon is a light element, meaning the electrons don't move fast enough near the nucleus to experience strong relativistic effects, which is what spin-orbit coupling really is.
So how do they get it?
To generate these topological edge states, you need strong spin-orbit coupling to break certain symmetries. So the engineers employ a chemical trick. They create a heterostructure.
A heterostructure.
Yeah. They take the bilayer graphene and physically sandwich it directly adjacent to a transition metal disalcogenide, or TMD. Specifically, they use tungsten diselenide, WSE2.
Tungsten is a very heavy metal. So by just placing the graphene physically flush against the tungsten diselenide, the carbon somehow borrows the heavy metal's properties.
Yes, through a quantum mechanical process called orbital hybridization. Because the layers are atomically close, the electron wave functions of the graphene and the tungsten slightly overlap. The graphene borrows the strong spin-orbit coupling of the heavy tungsten atoms.
Wow, it just leaches it.
Exactly. This borrowed property, combined with the magnetic field from our Halbach shell, triggers the Berry curvature, which ultimately forces those perfect one-way chiral edge lanes to open up.
It is absolute chemical wizardry. They are engineering an atomic city where the roads mathematically forbid traffic jams.
It's beautiful.
But this brings up a massive fundamental question.
Okay.
We have this 50 millikelvin levitating ship. It is perfectly shielded from the outside world by a magnetic Halbach sphere. The data is hidden in indestructible topological shoelace knots flowing silently down one-way streets.
Yep.
It is the most isolated, protected system in the universe. So how do we actually get the answer out of it?
The readout.
Right, because the golden rule of quantum mechanics is that if you measure a system, if you look at it too hard, the wave function collapses and you destroy the data. How do you read a topological knot without untying it?
That is the ultimate bottleneck for quantum hardware. And it brings us to the readout mechanisms and the grand scaling vision of the quantum sphere. Reading the state of a qubit without catastrophically destroying it via a clumsy measurement requires extreme finesse.
So what's their solution?
To achieve this, the quantum sphere relies on a trick called the Pauli blockade.
Pauli, named after Wolfgang Pauli, the physicist who came up with the exclusion principle.
Exactly. The Pauli exclusion principle is a fundamental rule of the universe. It states that no two identical fermions, like electrons, can occupy the exact same quantum state at the exact same time.
Right.
If they have the same spatial location and some quantum numbers, including their spin, they fundamentally cannot be in the same place. The universe forbids it.
Okay, I understand the rule, but how does the computer use that rule to carefully read the state of a qubit?
The white papers use a fantastic analogy to explain the readout architecture. They call it the revolving door.
Revolving door? Okay.
Imagine you have a double quantum dot. That's two tiny energetic potential wells sitting right next to each other on the chip. You have one electron trapped in the left dot and one electron trapped in the right dot.
Okay, got it.
The right electron holds your computed data. You need to know its spin state.
Right, but I can't look at it directly with a laser or a microwave without collapsing it.
Exactly. So instead of looking at the right electron, you manipulate the left electron. You apply a very tiny, precisely calibrated voltage pulse that essentially pushes the left electron, trying to force it to move into the right dot.
So you're trying to force two electrons to share the exact same physical space.
Yes. Now, visualize those two electrons as people trying to shove through a narrow revolving door at the exact same time.
Okay, I'm picturing the revolving door.
If the two electrons have the same spin, say, they're both spinning up, which physicists call a triplet state, they are identical. The Pauli exclusion principle kicks in. The universe says you cannot occupy the same ground state. The only way the left electron could enter is if it jumped to a higher energy state. But your tiny voltage pulse didn't give it enough energy to do that. So they bump into each other, the revolving door jams, and the left electron is blocked from moving. It stays in the left dot.
It's a blockade. The physics prevents the movement.
Exactly. But if the two electrons have opposite spins, one is spinning up and one is spinning down, which we call a singlet state, they are technically in different quantum states.
And because they are different.
Because they are different, the Pauli principle allows them to share the same spatial ground state. They glide smoothly through the revolving door together, and the left electron successfully moves into the right dot.
Oh, that is incredibly elegant. But wait, we still have to actually detect this. How does the computer know if the revolving door jammed or not without looking at the spins?
You place a very simple, non-invasive charge sensor, like a single electron transistor right next to the double dot system. Think of it like a simple security camera aimed purely at the doorway.
Just watching the door.
Right. The camera doesn't need to be highly advanced. It doesn't need to decipher the complex quantum spins of the people going through the door. All the sensor does is detect the electrostatic shift of an electron changing location. It only asks one binary question. Did a negative charge move from the left space to the right space, or didn't it?
That's brilliant. If the charge sensor sees movement, it means the door didn't jam, which means the electrons must have opposite spins.
Yes.
And if the sensor sees no movement, it means the door jammed, so they must have the same spin. You deduce the incredibly complex quantum state just by looking for a basic classical movement of electrical charge.
Exactly. And because measuring a shift in electrical charge is something classical electronics can do with extreme rapid precision, this Pauli blockade readout provides a digital measurement with greater than 99% fidelity in a single shot.
Wow.
It is fast, accurate, and because you aren't directly blasting the data qubit with energy to read it, it is relatively protective of the overall system.
So let's just step back for a second and look at what they have designed. We have a graphene chip. We can cool its electrons to near absolute zero using tunnel junctions. We can levitate it in a vacuum to kill vibration. We can protect its data for 30 seconds using time-reversing Kramers-pairs. We can perform fault-tolerant math by braiding topological enneins on one-way streets. And we can read the final answers using a Pauli revolving door.
It is a lot to take in.
It really is. That is a completely functional, highly advanced quantum computer in a basketball-sized sphere. But earlier, we teased the idea of millions of qubits. A basketball-sized chip can't hold millions of qubits. How do they take the single sphere and scale it up to actually beat the massive rigs from IBM and Google?
This is where we examine the ultimate architectural vision detailed in the documents, the quantum Dyson sphere.
This Dyson sphere.
To understand why this specific spherical scaling is necessary, we have to look at the fundamental fatal scaling limit of today's planar chips.
By planar, you mean flat, 2D microchips. Exactly like the silicon ones in our laptops and phones, and the current quantum chips sitting in those golden chandeliers.
Right. It all comes down to a concept in electrical engineering related to Rent's rule, which dictates how wiring complexity scales. When you have a flat 2D chip and you want to add more qubits, you have to route microscopic control wires to every single new qubit to send it instructions.
Okay, that makes sense.
As you scale from 10 qubits to 100 to 1,000, you have to run all those wires out to the edge of the chip to connect them to the outside world.
And a 2D square only has so much edge space.
Exactly. The 2D surface becomes an incredibly congested, unmanageable traffic jam of wiring. This creates severe physical bottlenecks. You literally run out of room.
Just physically out of space?
Yeah. And furthermore, crowding all those wires together causes electromagnetic crosstalk, where the signal from one wire bleeds over and interferes with the wire next to it, corrupting the quantum operations. It is a massive geometric limitation that plagues all flat chip designs.
A sphere. A sphere doesn't have edges.
It doesn't. The ultimate design of the quantum Dyson sphere scales by nesting. They propose taking 10 to 50 of these concentric graphene aerogel shells and nesting them inside each other, like Russian matryoshka dolls.
So you have a sphere floating inside a slightly larger sphere floating inside another sphere.
Yes, all connected by radial spoke planes made of bilayer graphene. This creates a true volume-based 3D architecture. Because you are utilizing the full 3D volume of a sphere rather than just a flat 2D surface, you completely eliminate the 2D wiring bottleneck.
How does that work for the wires?
You can route those microwave control signals from literally any direction, top, bottom, diagonally, via those 3D coplanar waveguides woven throughout the aerogel layers.
You completely bypass the traffic jam because you can route signals over, under, and around the qubits through the different nested layers without the wires ever having to cross each other tightly in a single plane.
Precisely. By utilizing spatial multiplexing across the volume of the nested spheres, this architecture targets a mind-bending density of 10,000 to 1 million physical qubits in a highly compact volume. We are talking about a structure just 1 to 2 meters across.
A million physically realized qubits in a sphere the size of a beach ball.
And we have to analyze the power efficiency of this scaled model because this is where the economics of computing completely shift.
Right, the power.
Currently, to run a 100-qubit planar system cooled by a massive dilution refrigerator, you are drawing roughly 25 kilowatts of continuous power.
25 kilowatts to run just 100 qubits.
Yes. The scaled 1 million qubit quantum Dyson sphere, because it relies on the highly efficient 4 Kelvin pulse tube cryocoolers and those superconducting tunnel junctions acting as heat siphons, is projected to use roughly 10 to 50 kilowatts total.
Wait, I want to make sure I'm doing the math right. You are saying they are proposing scaling from 100 qubits to 1 million qubits, which is a factor of 10,000 times the sheer physical size and an exponential, almost incalculable leap in actual processing power. But the energy consumption only doubles.
That's what the math says.
That is an exponential leap in power for a strictly linear increase in energy that entirely breaks the scaling laws of computing as we know them today.
It is an incredible projection. If successful, it would completely redefine the energy economics of high-performance computing. You wouldn't need a dedicated power plant to run the next generation of artificial intelligence or molecular simulation.
Okay, I have to step in here and play devil's advocate. I can hear the listeners yelling through their headphones.
Fair enough.
This sounds like pure science fiction. Let's ground ourselves in reality for a second. IBM and Google's flagships, as limited as they might be by wiring bottlenecks and massive dilution fridges, actually exist.
Yes, they do.
They are sitting in physical labs today. You can log onto the cloud right now and run rudimentary algorithms on them.
That is true. They are proven, verified, functional technologies.
This quantum sphere, it relies on a 3 to 6 month roadmap just for a benchtop prototype. And to get there, a single engineering team has to master diamagnetic levitation, 3D printing of pure graphene aerogels, femtosecond laser reduction fabrication, local tunnel junction electron refrigeration, and topological Ennian braiding, all at the exact same time, successfully integrated into the exact same microscopic device.
That's a tall order.
I mean, isn't this just a beautiful, highly optimistic concept that only exists on paper right now?
It is entirely fair to be deeply skeptical. It is absolutely a conceptual design integration at this stage. But here is the crucial counterpoint that makes these white papers so compelling to the scientific community.
Which is?
While the integration is highly ambitious, not a single piece of the underlying physics is science fiction. Every individual component relies on peer-reviewed, demonstrated laboratory science.
So the individual pieces of the puzzle actually exist. They're just trying to build a completely new box to hold them all together.
Exactly. Direct ink writing of graphene aerogels is a proven manufacturing technique today. Bilayer graphene gate-defined quantum dots have been successfully built and tested in labs.
Right?
The physics behind a 30-second Kramers-pair coherence time is based on actual measured experimental physics regarding spin-valley coupling. Selective electron tunneling for localized cooling has been successfully demonstrated in graphene devices. They aren't inventing new laws of physics to make this work. They are proposing an unprecedented, audacious feat of engineering to integrate known physics into a single architecture.
It's a moonshot. But it's a moonshot based on actual orbital mechanics and material realities, not magic. And that brings us to the end of our deep dive. Let's briefly recap this incredible journey we've been on through these documents. We started with the old paradigm. Bulky golden chandeliers draining tens of kilowatts of power just to keep flat, congested chips cold.
And we explored the proposed alternative. A 3D printed, completely levitating graphene processor encased in a magnetically shielded, laser-etched Halbach sphere.
A processor that literally cools its own data carriers using superconducting tunnel junctions, allowing it to sit in a relatively warm room. It stores quantum data for a staggering 30 seconds using time-reversing Kramers-pairs.
It performs fault-tolerant calculations by braiding topological knots of Ennians on one-way chiral edge streets.
And it reads the final answer just by watching electrons bump into each other in a Pauli revolving door before scaling up to 1 million qubits inside a nested Dyson sphere.
It is a profound, holistic rethinking of what a computer can look like, how it dissipates heat, and how it can operate free from the noise of the universe.
And I want to leave you, the listener, with one final, incredibly provocative thought. We didn't even get to discuss this fully as it was just a footnote in the scaling section. But buried in the design documents is a mention of a future material. It's called magic angle twisted bilayer graphene, or MATBG.
Yes. This is a phenomenon that occurs when you take two sheets of pure graphene and stack them, but you twist the top layer relative to the bottom layer by an incredibly specific angle, exactly 1.1 degrees.
1.1 degrees. And when you achieve that exact geometric twist, the documents note that this pure carbon structure exhibits intrinsic superconductivity. Because the offset creates a moire pattern that perfectly flattens the energy bands, the carbon becomes a superconductor all on its own.
It means that in a future iteration, the processor wouldn't even need the aluminum tunnel junctions or the heavy tungsten dislonide dopants to achieve these incredible topological states and cooling effects.
I want you to imagine that future iteration of the quantum sphere. What happens when humanity learns to build a fault-tolerant, million-qubit topological supercomputer? Out of nothing but geometrically twisted, pure carbon. No heavy metals, no rare earth magnets. Just the exact same element, the exact same fundamental building block that makes up the human body. Just pure carbon, perfect geometry, and the laws of physics.
It suggests a future where our most advanced computational tools are no longer massive, resource-heavy industrial machines, but are seamlessly integrated with the most fundamental, abundant materials of the natural world.
It's breathtaking to think about. Thank you for joining us on this deep dive into the source material. As you go about your day, the next time you look at a silicon microchip, or even just a pencil tip full of graphite carbon, remember, the future of computing might look a lot less like a flat, wired board and a lot more like a macroscopic levitating sphere.